So what we are going to do is that we're going to do all the analysis, everything in R. Okay. So this is a data set. Okay, I'm showing you the data set here. And watch the way I've labeled the data set. I have called it DMU A, B, C, okay. And this A, B, C, I have them in year 1 and then in year 2, but I've not indicated the years. But the fact that we have this here will give you the clue in year 1 and then in year 2. So I have it here. I'm just going to take this data and take it to R. So I copy this and then I take it to R. Now watch carefully. You will see that this one, I've labeled it as DEF because I want to draw. So if I want to draw, I want to use different labels for them. But if I'm going to estimate the productivity, I'll come back and come and use this. So let's take this first one. Watch how I've labeled it. It is A, B, C, D, E, F. Take this and go to your R Studio. So I am at my R Studio. Can you confirm if you can see my R Studio?
Yes, Doc, it can be seen.
Good. So this is the R Studio. I'm going to load the data with this command. And of course, you have all of this in your slide, by the way. This is the data set down here. You see the data set down here. This is it. That's the data set down here. Okay. Now, what we can do is that we can now remove the first part of the data, the first column. And when I say the first column, this DMU column, we're going to remove it, okay, and then bring it back and replace it with the row name. So they are going to rather replace that first column here. And then I can show back. I called it P, so I can show that P. And you can see that this P is the DMU names are replacing the first column. All right. Now we create an input matrix, okay, that is in year 1. So I'm calling it X1. That's an input matrix in year 1. And remember, it is a column bind of the X1 and then X2, the input 1 and input 2. So this first X1, the 1 here is year 1, but then the 1 here is the name of the input 1. So take note of it. And then the Y1 is the year 1 output. And then I can create the year 1 DMU, then go to year 2 input. Okay. The year 2 input is made up of X1 and X2 inputs, about combining them to make year 2 year 2 inputs. Okay. And then I do the same thing for the output. Then you can create the DMU. All right. So let's for example look at X1. That is year 1 inputs. Watch it. Okay. Those are the 3: DMU1, DMU2, and then DMU3. Those are the input X1, input X2. And then when you go to the year 2, okay, this is what you get. Input X1, okay, for the first column, input X2 for the same DMU. But I'm going to do a drawing. Okay. I'm going to use benchmarking as a package to do the drawing. So you invoke the benchmarking, and then you draw the first isoquant. So this is the first isoquant. Remember, I've renamed it. When you look at the codes later, you see that I have given them different colors of them. I will add the names of the DMUs to it. Okay. So this is it. Just as I told you, this is DMU A, this is DMU B, this is DMU C. Then I can draw the second one. Okay. The second one is the second isoquant. Okay. And I'm sure you guys can remember this was in the Excel. I just want you to know that R can do what the Excel did and even more. So it's able to do that. We don't need to label those DMUs, okay? But you can. But I gave a different name for it. If you can remember, I called it DMU D, F, and E. So those are the names that you are seeing me do it. Because I just didn't want to call it B1 and then now B2. Okay. But you should just know that D is for the DMU A in year 2. E is for DMU B in year 2. F is for DMU that. Okay. So that is how you do the drawing. That's all. Okay. You can draw the radial lines and all of that. But again, it's not too key. The most important reason why we are here is to come and estimate the productivity scores. So to do that, we go back and take the data set as it's supposed to be. Remember, I told you that we use this one for graph. Now I'm going to take this one. Okay. And watch it. They are not EFG. Okay. They are not DEF. They are ABC in year 1 and year 2. So I take this data, I go and load it. I'm about to load it. But before I load it, you got to install the package called FEAR. How do you install the package called FEAR? There are 2 ways. You can go to packages and then click install and then type FEAR. Okay. If you have an internet, it can show. If you don't have an internet, it might not show. Sometimes it's not even there. And so when it is not there, let me see whether it is there. Yeah, it's not there. Okay. So there's another way. You have to install it from the Professor Wilson's website, or Wilson, which I have indicated in my video, in my other video. So if you go to the channel, you can see my other video. And then it will show you how to get it. But let me see if I can quickly show you if it is available. So what you can do is that you can type here. Okay, this is the website that I went to. But you can just type here for Wilson and just check. Okay, so this is the great man himself. You can go to the bottom of his page and you will see FEAR. This is it. Okay. And then just click on that FEAR. It will bring you here. And then you can now click on the current FEAR, this one here. Okay, click on it. And then you accept the license. And then you can come and then download this package. Okay. It has an installation instruction. It has, manual, and then it has the package for both Mac OS, Linux, and then Windows. The Windows is the first one. So if you have Windows, let's assume we all have Windows, you take the first one. It is a zip file. Okay, so you can save it in your folder. Let's call it, let me just save it here. I have another one which already exists. So let me override that. So the thing is in the folder. It's loading in the folder, it's loading, pop, it's done. Then when you open the folder, you can see it. But now let's go back to our package, where you had a package here. Please, do you see where you have the package? Do you see what I'm showing you now? Do you see the arrow?
Yes, Doc, you can see.
Okay. So when you are the arrow here, you will now click on where you have repositories CRAN, where you have the install from. And then instead of the repository, you choose the package archive. And once you choose the package archive, it will direct you to go to your folder. Then you select the folder where you had a zip file. Okay. So I've clicked the folder where I had a zip file. You can click and arrange by date modified. The zip file is right here. Okay, it's FEAR, Frontier Efficiency Analysis in R. Just double click and it is opened. Okay. That package is going to show here. And this is what is showing. It's showing down here. Once you have this, you can now click install and R will be installed. I have installed already. I don't want to do it again. Okay. And then once you install, you'll see it populating themselves nicely on the blue background console here. Then you get it installed. Then this will go up. To see that R has been installed, come to the search here and type FEAR to see that FEAR has been installed. type FEAR here, and you see FEAR, which means that it's been installed. So apart from benchmarking, FEAR is a powerful package, and it has this advantage over benchmarking. That we'll talk about later. So let's assume that we've installed FEAR. I'm going to now run the FEAR. It's the same as searching for it and clicking this box. But instead of that, you can do a library, invoke it. So let's run the library. Once I run the library, you see it down here. Okay. Of course, it's slightly competing with the benchmarking, but no problem. I have my data. Okay. I have my data that I copied, the new data. So let me load that data. In order to see the data, just look down here. It has ABC, ABC. You can create an input and output matrices for the data. Let me do that quickly. Okay. I even created a global one where you combine the year 1 and year 2 as well. So let me just show you what I mean by the global. This is a global input. This is a global output. Okay. That's it. You're done. Okay. Remember, we don't need a global here. Now we are going to use this command called PM, Malmquist.component. Then you take the transpose of the inputs in year 1, transpose of the output in year 1, the name of the DMUs, then the transpose of the input and output in year 2. Then you indicate whether you're doing bootstrapping. Then you select NREP, number of replication. We are not doing bootstrapping. So the number of replication is 0. You leave it there. Then you indicate whether you're doing input-oriented or output-oriented. If it is output-oriented, it's 2. If it is input-oriented, it's 1. If it is hyperbolic orientation, it is 3. So we are going to run that. Let's run that. Now, how do you know the results is shown? Just go and highlight the results, just as I've done. And then you can see the results all down here. So why is this results powerful? It gives you the efficiency score. Oh, it gives you the distance function for each DMU. And it gives you for both VRS and CRS. Okay. So for VRS, watch it. You get this. You get 1 in year 1. If you can remember, A and B were all efficient. And remember, this is distance function. So the scores are greater than 1 for inefficient ones. And then for VRS in year 2, you get the same thing. A and B were still efficient. C was still inefficient, as you can see. And then the cross periods for that. And then the constant returns too. You get all the scores. So it gives you both constant and then variable returns. That is it. But let's get to the components itself. To do that, you run this command. I chose PMR. And just write Malmquist into bracket list PM, where the PM is the one you ran before. Run that, and then go and see the results. And it's beautiful. And it's beautiful. Look at the results. So the results here will give you the Malmquist productivity score for each DMU. So watch, DMU1 has got a Malmquist productivity of 1. That's what we had before. DMU2 has this. DMU3 has that. Of course, it is input orientation. So to get the scores, you have to take the reciprocals, as we know. We shall do that very soon. Then you have the efficiency change. Take note. This efficiency change. And that constant returns. And that constant returns. Then you have the technological change. And that constant returns. And that constant returns. Then you have the pure dot efficiency change. So that is the pure efficiency change, which is efficiency change and the variable returns to scale. So that is a PEC that we saw in the formula. Then this scale is a scale efficiency change. I'm giving you this name because I know them. Okay. The scale efficiency change, which is a SEC. That is a scale efficiency change. Then you have pure technological change. That is a PTC, a pure technological change. Okay. And then you have scale technological change. That's the STC, which we have. Then the Ray and Desley one. Remember that scale change? That one is here. So it gives you all of these changes. You can now create a data frame from all of them. So I've decided to do that. So I call MC, let MC be the Malmquist score. Let EC be the efficiency change. Let TC be the technological change. Then the VRS score. Now, I created a VRS score because VRS is just the pure efficiency change times the pure technological change. That is a VRS score. I created that here. That's a new thing I created. And then the pure efficiency change, I told you, you pick it. You pick it, this is it. And then you indicate where it is collecting it from the data frame known as PMR. And then you also write the pure technological change. That one you select it from the previous graph result I showed you. Then you have the scale efficiency change. That one you select. Scale technological change, I called it STC. I'm renaming it. That's it. And then the scale change finally. You can now round all the thing to 3 decimal places. Now look at the answer. Is it not beautiful? So at the bottom here, you have all the answers for all the Malmquist and the components. You have them all here. The Malmquist, the efficiency change and the constant, the technological change and the constant, then the Malmquist and the variable returns, efficiency change, and the pure technological change and the rest. You can also get the parts in efficiency terms instead of distance function. So this time I added the part and then brought everything together. Oh, again, you can check it later. This is the final result. So watch this final result. If I should squeeze this thing to the right here, you can have all the results showing at one go. Let's do that. In one horizontal frame. That's it. So watch it. These are the efficiency scores. Remember, I took the reciprocal there. Okay, I took the reciprocal. Okay, I recalculated it. Take the reciprocal. So that's a constant returns, the 4 different constant return score. That is a 4 different variable return score. Then the Malmquist and the constant returns. Then the Malmquist and the variable returns and all the parts. It does it all for you. If you were doing bootstrapping, it would have done all of that as well for you. So you get the same, as you can see, you get the same results like the one we hand calculated. And in actual fact, when you are doing your normal work, your thesis, your journal article, your practical working for companies, your consultancy, anything, project, this is the way you are going to do it. You get all of this. So the rest has to do with interpretation. Okay? So you use your interpretation to now interpret the score and make the score clear. So when you look into the slides, I have all of these there. Okay? Everything that I want to take your time, we will go through them, run each one of them. I did it for the benchmarking. I did it for the R. Okay? In fact, you will see that I've done both for you. The disadvantage about the benchmarking, if you use the benchmarking package, is that it doesn't give you all the 4 parts. It gives you only the 2 parts of the decomposition. It doesn't give you the skill parts. And so normally I do not like using that a lot. But other than that, if you use this one, you get some very beautiful work running there. Okay, any question? Now let me go to the final drift for today. The final drift for today. And it is known as a concept of innovators. And please, I want you to pay attention to this because you do it, and you need to do it in your thesis. You also get it in your exams and then everywhere. Which DMUs shift to the frontier? Which DMUs are the movers and shakers of the industry? Fair Groskop, Norris and Zahn, 1994, introduced the concept of innovators. Okay. And if you identify the same innovators every year, it can give you an extra indication about those firms that invested in R&D. Those firms that invested in product innovation, process innovation, learning by doing. So if a particular firm is appearing every year as an innovator, that's good. And one unique thing about those innovators is that they are the ones that define the efficiency of the other guys. An innovator DMU, an innovator firm is the one that defines the frontier. So other people's performance are relative to that innovators work. So how do you tell that a firm is an innovator? Well, you can use the technological change to tell whether a firm is an innovator. How do you do that? How do you do that? Well, what happened to the frontier at the input level and then the mix at each DMU, but not if that DMU actually shifted the frontier. So when you take technological change will tell you, the value of that DMU when the industry changed, when the industry shifted, when the frontier shifted, the technological change score will tell you how that firm became. But it doesn't tell you which firm shifted the frontier. You know that some of the firms will not shift to the frontier, but they will take advantage of the technological spillovers. I'm sure you know that. I remember telling you the story of the Samsung and then the Apple iPhone. iPhone was an innovator. Apple was an innovator of the touchscreen environment. Samsung was not really that much of an innovator, but took advantage of the technological spillover and started rubbing shoulders with iPhone. Today, they are doing well. BlackBerry didn't want to take part at the time. Nokia didn't want to take part at the time. Today, they have plummeted in their stock pricing. So you may not be a shifter of the industry, but you could be an opportunist, an advantage taker of that shift. So to get those shifters, those movers and shakers of the economy, you got to look deep into the technological change. Let's look at it, the formula. For a firm to be an innovator, and we are assuming that the indices here are greater than 1, okay, for progress. So you got to use the greater than 1 for progress 1. That is after you've taken their reciprocals in an input orientation. Okay. Now, and that will mean that if the firm is a super efficient firm, the score is going to be greater than 1. That's what it means. So if the firm is an innovator, there are 3 things you will notice. 1, you will notice that the pure technological change of that firm is greater than 1. That's the first one. The pure technological change of the firm will be greater than 1. And like I said, after you've taken those reciprocals. 2, the cross-period efficiency of the firm in year 2 relative to frontier 1. That is, when the firm was in year 2, its score relative to frontier 1 should be positive. Now, this means that that firm should be super efficient. That's what it means. It simply means the firm should be super efficient. And of course, if it is year 1, if it is an output orientation, so look at it. Output orientation, the scores are greater than 1. So in that case, the firm super efficient score should be less than 1. That's what I've indicated here. So that's the second point. The firm should be super efficient. The third one is that the own period efficiency score of the firm should be 1. Own period should be 1. Own period efficiency score in year 2 should be 1. A cross period super efficient in year 2 should be greater than 1. And I'm talking about input orientation. And finally, the pure technological change should be greater than 1. So let's look at in our 3 cases and let's see. Okay. So look at DMU A. Okay. I look at the own period efficiency score in year 2. This is the own period efficiency score in year 2. And the rule is that it's supposed to be 1. It is 1. Okay, so it passes one of the first. B, own period efficiency is supposed to be 1. It is also 1. C, own period efficiency is supposed to be 1. It's not 1. So we'll start with A and B. So A and B are likely to be innovators. But let's move forward to the second criteria. The second criteria is that they are cross periods. They are cross periods in year 2. This is cross period in year 2. Cross period in year 2 relative to frontier 1 should be greater than 1, should be super efficient. Their cross periods should be super efficient. Now, DME-A cross period is not super efficient. DME-B's cross period is super efficient. B is winning. We just have one more thing to check. And it is the fact that the technological change or the pure technological change should be greater than 1. This is a pure technological change. The pure technological change is truly greater than 1. Therefore, the firm that is the innovator in this industry is firm B. Firm B is the innovator. But as you all know, firm C took advantage of firm B's innovation. And therefore, firm C also looked very good eventually. So that is how you determine, productivity and innovators. Learn it. We have looked at several decompositions of the Malmquist index. Aside the Wheelock and Wilson decomposition in 1999, the other ones, Zofio did some further decomposition. They also did a 4-factor decomposition. Others have pursued 4-way decomposition. Gilbert and Wilson, Simmer and Wilson, they've all done that. Greffel, Taji, and Lavelle in 1999 did a generalized Malmquist productivity. This is in another package, which is called DEAR. In fact, Lavelle summarized all of these and then created a very interesting 7-way decomposition, which he does not recommend that people use because of the extreme difficulty of it. Because he's not able to distinguish the output mix change and the input bias, those things that I spoke about. So he showed a 5-way decomposition rather. And he also showed that the Ray and Desley decomposition, that one is simple, but it can compromise some interpretations of the scale efficiency change, as we know. But guys, the ones I've given you are useful, and those are the ones that you want to be using in most or all of your research. Aside the Malmquist productivity index we have considered here, there is also something we call the Hicks-Mustin productivity index. It's by Jurek and Bob. Go and read a bit about it. And Leuenberger productivity indicator, that is very useful for those doing directional distance functions. If there is time, we'll look at that as well. Yes, so the other decomposition, for example, we have those in the parametric literature. Shimizu and Page decomposed the stochastic distance function and created a Malmquist productivity in the world of stochastic frontier analysis. All of these are to tell you that there are other interesting things that are there. Okay, so that brings us to the end of the entire caboodle. What a day it's been. So at this stage, I know you all have several questions you're going to ask. Let's look at the questions that